Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're going to be talking about Torricelli's equation, or Torricelli. And the idea here is very simple yet very powerful, because Torricelli basically derived an equation that is capable of finding the velocity at any given time without relating time. So basically it's a way of finding the velocity at any given time based on the position of the given object that you're trying to find. So it's pretty interesting. It's very useful. I'm sure that you as a student have used this before, but the idea of this video is like talking about where it comes from, and from that exercise to think about where it can be used, where it cannot be used, right? As per usual, we start with the very fundamentals, and the very fundamentals are that the velocity is just the rate at which position changes with time, right? And the acceleration is just the rate at which the velocity changes with time. And here we already see the idea behind this equation, which is basically we have two definitions of velocity and acceleration, and they both are bounded, or both are dependent on time, right? But if that's the case, what I can do is combine these so that I can remove the time component. So basically what I want to do here is solve for time. And I'm going to start by changing this guy here into, okay, so this means that my A times my dt equals dv, and therefore dt is just the dv divided by A, acceleration. Okay, with this here in mind, I'm going to then substitute where I have dt over here, right? So basically this guy here is going to become this guy here. And what does this do to our equation? But basically then says that the velocity is dx divided by dv divided by A, so A comes up here. Okay, and if that's the case, now I have something very interesting, because now I can solve for A, and what I'm going to see is, if I solve this for A now, I'm going to see that A can be defined as the velocity times the rate at which the velocity changes with x. And I'm running out of space, so let me go ahead and put this down one section. There you go. Okay, so this is a very interesting definition for acceleration, one that we're not generally used to seeing, right? Again, we didn't do anything wrong here. We just found a new way to express the acceleration, which is to say that the acceleration is equal to the velocity, and this velocity is changing over time because there is an acceleration, and how the velocity is changing, not in respect to time, but in respect to the position. How does velocity change as the position is changing? And remember that the position is changing with time. So we didn't get rid of time completely, but we got rid of time as a way to express the acceleration. And with that, now what we can do is solve this for any position that we want. And with that, we can find Torricelli's equation. So basically, I'm sending dx to the other side. I'm going to end up on the right-hand side with v dv. And here comes the integration. And this is a very interesting integration to do, because there's one thing we need to observe very carefully. Once again, we can do this with defined integrals or undefined integrals. It's up to you. If you do undefined, you're going to end up with a constant. That constant you can solve for when the x is x naught, so when the position is the starting position, that will be v naught. But the other way is just to do defined integrals as we go from x naught being the original position to any position that I'm interested in, and from the velocity being original velocity to any velocity that I'm interested in. In that integral, then we have something very interesting, which is if this acceleration is dependent on the position, that is, if the acceleration is changing, then I cannot solve this integral right here as simply as I want to, because what I want is basically to remove this acceleration from my integral and be left with acceleration times the integral as I go from x o to x, and that's going to be dx, and then on the right hand side nothing changes, v naught to v times v dv. Okay, very important. This step here that we just did of removing the acceleration from the integral can only happen if acceleration is a constant, right? And if it's not a constant, then this cannot be applied. So that's already a restriction that we see on Torricelli's equation. This is only going to be true if my acceleration is a constant. Okay, now if we integrate this, we're going to have acceleration times the x minus x naught, also known as delta x. And here on the right hand side, I'm going to have the integration of v, which is going to be basically v squared over 2 minus my v naught squared over 2. They're both divided by 2, so I can have a single 2 here that divides both, like so. And now you can already see it's taking the shape that we want it to have, right? So acceleration times my delta x, and I can go ahead and send and multiply on both sides by 2. So I can multiply by 2 here and by 2 on the right-hand side, which will basically eliminate my 2 from the division. And this is already has the shape that we wanted to. 2 times the acceleration times the delta x equals v squared minus v naught squared. And therefore, if I solve this for velocity, I'm going to have v naught plus 2 times the acceleration times my delta x, which hopefully matches perfectly with our proposition in the start. Okay, so this is how the equation comes to be. The whole idea behind it is that it's an equation that you can use when you don't have the time component, when you're not given time, so your problem statement does not give you time, but you have acceleration and you have original velocity. You can go ahead and calculate the velocity at any point given the position, right? Another form of this equation that you may see is when we're talking about something going up and down vertically and the only force acting is gravity, then this acceleration basically becomes gravity. And one form that can take place is one thing before that is often this is portrayed as we take the square root over here, and therefore this can also be portrayed as the square root of v naught plus 2a delta x. No mysteries there, but this is another way that you can see this equation happening. And another form that you see this equation often taking place is, like I was saying, when you have a vertical object going up or down, and the only force being applied is gravity, then the equation is going to be basically v equals, if I'm keeping it that way, the 2 times, then gravity takes place of the acceleration, because that's the only acceleration we have in these types of problems, and it goes like so. And yet another simplification that often happens is if this object is at rest when time is 0, so before the problem starts or before the action takes place, it's at rest, then obviously this component goes away and you have a simplified form, which is the velocity is just going to be the square root of 2 times gravity times whatever distance this has traveled. So this is very interesting because this is a way for us to capture velocity in any given position. So if you think about an object that's starting over here and it's going downwards, then all you need to know is how much has it gone downwards in this arbitrary delta x that we're creating to know what's the velocity by multiplying the gravity times 2 times that delta x and taking the square root. That allows you to capture the velocity at any given position. So this is the Torricelli's equation. This is a very useful equation. Now you know where it comes from. Now you also know that all of this, everything we talked about so far, is only valid when our acceleration is constant. If it's not constant, then you cannot use these equations, these formulas. The other thing that I want to point out before closing off is there's actually a way to obtain the Torricelli's equation without doing any integration, which is very interesting. So if you are at this point here, right, what you can do is, instead of doing it in the differential form, you can just say that your acceleration is going to be the delta v's divided by time. So actually, this is not true. I'm coming from this definition here. So over here, so delta v is going to be divided by delta time, so velocity minus velocity initial delta time. And what you can do is from here you can relate this delta time here with the position that the equation that we derived on the last video, if you want to check that one out, which is just the position equation, the general one, x naught plus v naught t plus a t squared over 2. What you can do is you can solve for this t squared here, and you can square this equation here and substitute it in, and you can end up with the same exact Torricelli's equation without having to do any derivation. So as an exercise for you, you can go ahead and do that. Interesting exercise, going to get something out of it, and obviously you should arrive at exactly the same equation as Uncle Torricelli did. So if this was helpful, consider giving this video a like. If you have any questions, as per usual, just leave them down below in the comment section, and we'll talk soon.